So we continue with our discussion on the graphite oxidation problem. And if you remember, I have drawn a hypothetical container which is sealed at one end, and this is the graphite block. This is the length, and we have a carrier gas here, and maybe you can say that the oxygen diffuses here, carbon dioxide goes out there, and then we have a case of equimolar counter current diffusion, as I have indicated. And this block has a surface area, which may be, if you look at from this end, is a circular cross section, so pi r square. So the area is known. So exposed surface area is A. So as I have indicated, there are essentially two kinetic steps in the whole process. Number one is that oxygen from the bulk has to diffuse, and this diffusion takes place because of concentration gradient. And once oxygen reaches the surface, the temperature and pressure are favorable that this particular reaction, carbon solid plus oxygen gas, produces carbon dioxide. And then the carbon dioxide is generated at the interface, at the reaction site, and the third step is the diffusion of carbon dioxide from the reaction site to the bulk. Again, this takes place because of concentration gradient of carbon dioxide, because carbon dioxide is being swept here, concentration is 0 here, and concentration is dictated in accordance with the equilibrium, as I have indicated. Now, because the fluxes of oxygen and carbon dioxides are equal and identical, so we can say that the entire process of graphite oxidation can be boiled down into two different kinds of kinetic steps. One is a mass transfer kinetic step, which essentially is the diffusion of the gases, and the second is a chemical reaction. And then the diffusion part has two different components. One is the reactant diffusion, the other is the product diffusion. Okay? So we want to now calculate, we have assumed yesterday, as I have indicated, that the rate of reaction, this is now can be treated to be very fast, it is high temperature, and this reaction can be taken to be at equilibrium. And this allows us, this equilibrium consideration allows us that we should be able to find out that what is the value of PO2 and PCO2 at the interface, okay, where this reaction is occurring, because the value of K is known to us. So therefore, I would say that the interface concentration of PO2, let it be denoted by star, and PCO2 also be denoted by PCO2 star. So these are estimated values on the basis of known equilibrium constant, which is known from temperature. I repeat again, and that the total pressure is equal to 1 atmosphere, that is equal to PCO2 plus PO2, and that's equal to 1 atmosphere. So we can get the value of PO2 star and PCO2 star, which is prevalent at this. And this value is satisfied everywhere. So here also it is 1, here also it is 1, here also it is 1. So therefore, I should be able to find out exactly that what is the interfacial concentration of CO2. So therefore, I would say that the oxygen concentration, and as I have also indicated that once you know the partial pressure, you can also find out the CO2, because PO2 divided by RT will give you in accordance with the assumption of an ideal gas behavior. Okay? So if you can calculate the PO2 star, so you will be able to calculate the CO2 star, the concentration of oxygen in kg per meter cube, and this is equal to N by V actually, as you all know, number of moles of O2 divided by the volume. Okay? So it's number of moles of oxygen per unit volume, and that is given by that expression. So we know the CCO2 here, which is CCO2 star, and we know the CCO2 here also, because this may be a 50% argon oxygen mixture or maybe a pure oxygen. So therefore, PO2 can be 1 or PO2 can be 0.5, and this information is known to us because it's the boundary, this constitutes essentially the boundary, okay, at x is equal to 0 maybe, I would say here, and x is equal to L if my x is in this particular direction. So therefore, I would say that the expression of NO2 will be basically JO2 multiplied by the area, and because it's a steady state diffusion case, so therefore the JO2 can be given in terms of D, okay, and then we can say that this is equal to into A0, and then this is divided by L into CCO2, so that is equal to PO2, so you will say LRT, and then we can say here PO2 star minus PO2, and this is represented by PO2 bulk, which is the concentration of PO2 at this. So that's what is the rate expression that determines the flux of oxygen, okay, and total rate of oxygen in kg moles per second, so that is the unit. So this essentially indicates that as far as this equation, so many kg moles of oxygen is going this way, so many kg moles of carbon is being oxidized, and so many kg moles, an equally identical number of carbon dioxide moles are being generated. So this is an application of the generalized diffusion equation, which I have indicated yesterday, that the diffusion flux C D mole fraction is equal to Na minus Xa into Na. I will write always two component systems because we are considering not more than two multi-component systems we are not going to analyze in this particular course. So this generalized equation, considering the case that Na is equal to minus Nb, or the flux of oxygen and flux of carbon dioxide are equal and opposite, so this term vanishes, and then on the basis of solution of this particular equation, mass balance, then we can determine that this is the standard slab geometry solution, as we all know, okay, concentration diffusion coefficient multiplied by the concentration difference divided by the distance over which the diffusion takes place, and RT manifests here because of the conversion of units. So an expression can be found out. Let us now move on to a different topic, and that is, we know that what is a steady state diffusion, because I have written this equation that if you write, for example, in the case of solid, and then one dimensional unsteady state equation, and we say that this applies, x being the direction of the equation, and there is a net rate of accumulation in the system. So when this term is equal to 0, in that case the diffusion becomes steady state. I have discussed extensively that when nothing in the system depends on time, we will call it a steady state process. Okay? Now, and on the other hand, in the context of heat transfer, heat conduction, as well as convective heat transfer problems, I have shown you, or we have discussed, that we have steady state heat transfer process and unsteady state heat transfer process. We have not talked about a class of process, in this case, which is very significant, or pseudo-steady state. It is in between steady state diffusion. One important thing you must have noticed, that I do not know whether you have realized this part or not, that when you have this carbon block here and the oxidation of carbon is taking place, at time t is equal to 0, we have a thickness of the graphite block. But as time goes on, then what happens? The thickness changes. Now, if this thickness is very small in comparison to the overall length across which the diffusion takes place, then of course the change in the thickness of the object or the graphite layer is not so important at all. But nonetheless, as a function, as carbon starts getting oxidized, the thickness changes, and as the thickness changes, the domain length changes, and therefore we can say, fundamentally speaking, the process is not quite at steady state. So this pseudo-state, steady state diffusion is actually an unsteady state diffusion process, but we will see that our knowledge of steady state fundamentals can be applied in a pseudo-steady state problem. For example, I can say that imagine that we have a nickel block which is subjected to an oxygen atmosphere, okay, and this is my, and it's at a high temperature. So what happens that once this solid nickel at a temperature T is exposed to an oxygen amine, so we have a reaction like nickel solid plus oxygen gas, and that gives us nickel oxide, which is in the solid phase. So we'll balance it. That's what it is. And this reaction takes place at this interface at time t is equal to 0. Now imagine that we have started the process, we have brought nickel in contact with oxygen at a temperature of T, temperature is constant, Pt is also 1 atmosphere, it is constant. And now after a time t, what is the scenario? After a time delta t, so maybe say 1 hour or so, and you can expect that there is a nickel oxide layer which is forming, because if you leave this nickel in oxygen pure, you keep on supplying pure oxygen, then what is going to happen to nickel? Nickel will spontaneously oxidize, and then the entire nickel block will get transported or transformed into solid nickel oxide as part of this reaction. So this is the product which forms at time t is equal to 0 at right interface. But after t is equal to 0, what happens when the product layer grows? Then the reaction interface changes, because now the interface is here, nickel is available only here. So the oxygen gas, if it reaches here, the problem, it is not enough. The oxygen gas has to diffuse through this solid layer, then reach here, then only it is, nickel is accessible to oxygen, oxygen can see nickel, and then only, because of thermodynamic conditions are. So the path over which diffusion takes place, so after another time you can imagine that this could be, if I draw it, break it, and then we can say the interface could be, so this is another, this is one thickness at small time, and this is another thickness which is at large time, because the product layer is growing as nickel diffuses, more reaction takes place, product layer grows, and as a result of which the path through which diffusion is taking place is continuously changing. It is nonetheless, as I have treated, suppose you assume that it's a very thick slab, so therefore it is a one-dimensional. Basically in this direction, this lengths and the lengths in this direction are very large, so therefore the diffusion is taking place in one dimension. So we have a case of one-dimensional mass transport. Now in this case, the length over which the diffusion or the path of diffusion is changing as a function of time. That's what. Okay. Now let us look at what is happening as far as the kinetics of the problem is concerned. Now the oxygen is exposed, this nickel is exposed to oxygen, so PO2 is equal to 1 atmosphere if the oxygen is pure is available, right? The oxygen concentration here is CCO2 is equal to PCO2 divided by RT, and PO2 is equal to 1 atmosphere, and then 1 divided by RT represents the concentration of oxygen. Then the oxygen diffuses. Now how does the oxygen diffuses? That is a topic that we'll address later on in some detail if you have time, but we must understand that the oxides, which is the product, has a different density. The metal is much denser, but the oxide is lighter, and as a result of which there are volume expansions, and as a result of which what happens is the density of the oxide is smaller than that of metal. There are cracks and crevices within the oxide phase through which the gas really diffuses. So unlike the platinum problem, where in pure platinum nitrogen was dissociating at the interface in according to the reaction. Here of course the oxygen as gas itself through the pores and through the tortuous path, which is the result of the cracks which formed because of the different specific volumes of nickel and nickel oxide, oxygen diffuses and oxygen arrives here. So the oxygen is available right at the interface, no problem. Then the oxygen gas will diffuse. This is the first step. Once the oxygen gas diffuses through the product layer at a time which is greater than 0, then oxygen can see nickel, and then this particular reaction takes place. So therefore I can say that the oxidation of nickel in an oxidation of nickel in an oxidizing environment or a pure oxygen environment will essentially comprise of two different kinetic steps. Number one, diffusion of oxygen through the product layer, oxygen gas through the product layer, and the chemical reaction at this nickel. This is the interface or the site of the reaction. We say nickel oxide interface. Okay, that is the site of the reaction. At time t is equal to 0, the reaction front is the one boundary of the solid. Okay, because oxygen can directly see nickel, but after some time, when the elapsed time is greater than 0, okay, then the oxygen has to make it available to nickel oxide interface such that this particular reaction can take place. Of these two kinetic steps, as I said, because we are dealing with diffusion and we assume that diffusion determines the rate, we will also solve a problem where with this equation, steady state equation, we will write the steady state version, we will write a reaction rate and we'll say diffusion multiplied by diffusion coupled with reaction, and how do you calculate the rate. But in this case, the rate of the reaction is not coming into the picture because the rate of the reaction has been assumed to be very fast. Okay, and as a result of which, what happens, this equation can be treated to be at equilibrium, which is at this particular interface, and therefore if you consider again the K value, this is going to be 1 by PO2, and this PO2 is the interfacial concentration of oxygen at this particular value. So therefore here PO2 is equal to 1 atmosphere, and here PO2 star is equal to whatever I have calculated on the basis of the equilibrium consideration. So the concentration, now the moment I say that look, my temperature is fixed, the value of K is fixed, so therefore the PO2 star, which is the oxygen concentration at the nickel oxide interface, is also fixed. So the concentration, the bounding concentrations per se are not changing. If temperature is constant, then the diffusion coefficient of oxygen through the oxide layer is also not changing. What is changing here as a function of time is the thickness of the oxide layer. So the problem, if you look at the problem, there are some parameters which are as if they are copied from the steady state problem. On the other hand, one single parameter is there, which is the length or the path of diffusion, which is akin to an unsteady state problem. So D, I would say D, not a function of D in this problem. Surface concentration, that is, I will say C star, not a function of time, but on the other hand, the diffusion path of is a function of time. So the path of diffusion is a function of time. The boundary concentrations, say C1, C star, etc., the way, okay, it is not a function of time. They are steady state because the moment I fix the temperature and pressure, state is defined, and similarly it happens with diffusion coefficient that it is not a function of. So of the three parameters of interest, two of them have a characteristics of the steady state process. On the other hand, this has a characteristics of an unsteady state process. So we can now analyze such a problem, and there is a good class of problem in metallurgical engineering literature, mostly oxidation, solidification. In solidification, what happens? The liquid transforms into solid. So the solid boundary is changing as a function of time, akin to this particular case. Oxidation, the product layer is changing. Similarly, if you take topochemical chemical reactions, which we will study later on, you will see that the phase of iron ore, for example, if you take iron ore, iron oxide, and then this is iron oxide, and then we have at some point of time getting reduced with carbon monoxide, then after time t, what happens is this iron gets reduced by carbon monoxide. So I will write solid, I will write gas, and then Fe solid. The product layer is growing as a function of time. So this is one scenario. After still longer time, the FeO will come here and the product layer. The path of diffusion, because the CO is available here, and the CO has to diffuse through this metallic Fe layer in order to reach this interface or this interface, which is the reaction side. Fe-FeO interface in this case is the reaction side, and in order to reach at the reaction side at larger time when the reduction has not been complete, carbon monoxide has to diffuse to the solid or the reduced metallic layer and make itself available. So this is also, as you can see, the path of the diffusion will be changing. In oxidation problems, in reduction, topochemical reduction problems, in solidification problems, in sintering problems, we will find that the concepts of pseudo-steady state diffusion can be applied to analyze the problems. Okay? So now let us see that how can you so we know that the flux can be written in terms of, in a one-dimensional context. So it can be written as, in this case, I would say CO2 bulk minus CO2 interface. And this represents the diffusion coefficient of oxygen through the product layer, that is through nickel oxide. D of oxygen through nickel oxide. As I have indicated, that I will write it now, that the flux is going to be a time dependent flux because of the simple fact that L, which I have assumed to be delta, okay, the path of diffusion is itself a function of the time. So you can see this diffusion coefficient is constant, this is constant as per our discussion. Okay? So only thing is that the flux is. So therefore I can say that the N of O2 you can see there the rate of oxygen, the flux or the net rate at which the oxygen is going on into the domain is exactly equal to the half, 2 times the nickel oxide rate of moles of nickel oxide production. So for every mole of oxygen, 2 moles of nickel oxide are going to be produced. So the rate of oxidation, or I can say that for every mole of oxygen, 2 moles of nickels are going to be. So if I can calculate the molar flux of oxygen, multiply it by a factor of 2, then I will get what? So many moles of nickels are being oxidized, per second. So we can calculate one single flux, and then the other fluxes can be computed based on the stoichiometry as dictated by the chemical reaction itself. So NO2, therefore, I can say that this is equal to minus D, and the interfacial area, which is fixed here. Okay, so you can imagine this is the volume element we are talking about. The diffusion, if the diffusion is taking place in this particular direction, okay, this represents the area, and that area is known through which diffusion. So it is A0, and this A0 is also constant. It is not changing. Okay, and only thing which is changing is the thickness, and this is equal to, I will write delta CO2, which is also not a function of time. So therefore, I can now say that this I will also represent as a function of time, because this is a function of time. So therefore, this parameter is also a function of time. And how have I applied? And we must, this is straightforward application of the steady state one-dimensional diffusion problem solution. But we must understand that we get now not a steady state flux, but an instantaneous, net rate of transport, and the instantaneous net rate of transport will be calculated. It can be calculated provided one knows that what is the instantaneous path of diffusion through which oxygen is moving. So this is kg moles per second, kg moles of oxygen per second. These concentrations are so there maybe you can say that CCO, because I have written concentration here, these are all molar concentrations, kg moles per meter cube, and then we have D into A0 is meter cube per second, second cancels out, okay? So we have, this is kg moles per meter cube, and this is meter cube, so meter cube cancels out, so this becomes kg moles divided by second, and that is the unit of NO2. So I write down that NO2 as a function of time is equal to dA0 delta C oxygen divided by. Now, this is the rate at which the oxygen is going. So now we can say that as a result of this oxygen diffusing through the solid, the product layer is changing. Now let us say that what is the moles of nickel oxide or mass of nickel oxide which is changing as a function of time. So we can say that this is equal to rho times area, which I have taken to be A0, okay, and then this is delta. So A0 times delta will represent the volume, and rho multiplied by rho, what is this rho? Rho of the oxide. So this represents basically it is positive because the mass is growing as a function of time. So therefore we can say that, and we can, if you consider it to be molecular weight, okay, the moles are moles, in that case we can say that because this is mass, so we can put the molecular weight of nickel oxide, and that molecular weight may be either MnIO. So this is the molecular small MnIO represents, and this is kg moles per second. Or because we represent, so we'll say dNO2 kg moles per second, and whatever I have written here. So the kg moles per second of oxygen, okay, this is must be equal to, and there are factor of 2 which is related. If you calculate from the equation, so this is going to be 2 times of N of nickel oxide. So kg moles of nickel oxide. For every moles of oxygen, 2 moles of nickel oxide is being produced, and this is the mass of moles of nickel oxide, rate of change of nickel oxide as a function of time. So therefore we can say that this, we have already shown here that this is equal to, from the right hand side of that equation is equal to d, and if we, because this I will not write as minus because I have already reversed the concentration gradients, okay. So therefore from higher concentration to lower concentration, so a minus sign is not necessary here. So therefore we can say that this is equal to dA0 into delta CO2, which is constant, divided by delta. Now we see here this. So what we get? We get if if we deal with the expressions which has delta here, so we will say everything is constant here. You see, rho is constant oxide, A0 is constant, molecular weight is constant, and so is d here, A0 here, delta C here, and this is equal to delta. Only function is delta. So therefore, we can say that we can write the equation as d delta, okay, into delta, and that is going to be is equal to dA0 multiplied by the molecular weight, which is NiO, okay, and then delta CO2, and then we have rho and A0. And this is equal to, you can say, beta into T. And if you integrate this, then we get delta square, okay, is equal to beta prime T plus C. Where C represents a constant of integration at T is equal to 0. What is delta? Delta is equal to 0. So therefore, we can eliminate this and write that the final equation therefore is D is equal to alpha into square root of T, which tells us that the thickness of the product layer changes as square root of time, and this is the famous parabolic rate law of oxidation. So as I have already indicated, that a parabolic rate law, this is for oxidation, a parabolic rate law where a fundamental process parameter changes with square root of T, or where T is the time, then you can say that the process obeys a parabolic rate law, and the processes of interest to us which obey the parabolic rate law are, the topochemical reduction reaction, oxidation, sintering, solidification, and so on. So this you must remember for all the time to come, that there are many processes which obeys, or which conforms to pseudo-steady state diffusion, and where we can mix and apply the concepts from pseudo-steady state as well as unsteady state, and then perform material balance to find out a characteristic equation of this particular form exhibiting a square root dependence on time. And if this condition is satisfied, then we say that a parabolic rate law appears to be dictating the process at the fundamental level. So before we discuss now, so we have talked about fundamentally steady state processes. We know unsteady state processes. We have also learned about pseudo-steady state processes. And the pseudo-steady state process particularly is significant in the context of diffusive mass transfer, where there is chemical reaction which is taking place. Had there been no chemical reaction, actually there would have been no product formation. So the pseudo-steady state reaction would not, be meaningful. So the pseudo-steady state reaction appears to us because with the diffusion there is a chemical reaction which are working in a coupled fashion. If it's the case of pure diffusion, no chemical reaction, then there is no scope for any pseudo-steady state reaction. And that's why, an analogous phenomena is not available, or we don't encounter in heat transfer process. Now, steady diffusion we have done. We will get back to steady state diffusion and solve the generalized equation of steady state diffusion maybe in the next class, but I want to introduce two different topics today. One is diffusion through parallel surfaces and uphill diffusion, and also if you have time, then we will introduce Kirkendall's effect also. And once we finish discussing this, then we will go to, for example, unsteady state diffusion, solution of steady state diffusion equations, and then unsteady state diffusion equations. Now, diffusion through parallel surfaces is very significant in the context of physical metallurgy, for example. So, we are not going to deal with in great detail, but I want to just introduce you to the material issue, some of the pertinent issues. We must understand that we have in a polycrystalline material, we have very different grains and when you treat a solid and where diffusion is important, so we have basically we can say that from here we can have basically a diffusion and taking place like this. Okay? So, this is the path of the diffusion I have drawn. Another path I could also draw is from here, for example, this is a possible path, for example. So, it is this. What is the straight path diffusion? Path of diffusion I have drawn. The other is a curved diffusion path, and as I have indicated in this polycrystalline material, this we call it as a lattice diffusion or diffusion through the bulk. On the other hand, this is diffusion through the grain boundary. So, this is basically J1 and this is J2. So, these are parallel diffusions. If material has to go through diffusion from here to here, these are the possible paths. Okay? Of course, essentially this could also go like this and come here, but that essentially is again becomes the diffusion through grain boundary. So, either it is diffusion through grain boundary or it is diffusion through the lattice. Now, so that's what he said, that in parallel diffusion through parallel surfaces means they are not essentially physically parallel, but they are parallelly occurring diffusion processes, okay, through two different medium, but in the same material itself. Now, the grain boundaries, as you all know, contains defects, and we all know that diffusion takes place or diffusion is promoted because of defects, and we have interstitial defects, vacancies, etc., and which promote. Had the material been perfect, every lattice site is occupied. In that case, there would have been virtually no diffusion at all. So, because the grain boundaries contain defects, as a result of which what happens is diffusion, even though the path seems to be longer, the diffusion is expedited through the grain boundary. And in the analysis of the relative diffusion rates through grain boundary and bulk, which is of interest to the physical metallurgy, a simple analysis through diffusion through parallel surfaces can be made. And in that context, I just want to introduce a parameter called the effective diffusion coefficient. Effective, I just introduce to you that you may have come across this term. So, for example, fundamentally speaking, if you take a two-phase steel containing 100% perlite, for example, and perlite, that it contains two different phases, ferrite as well as cementite. So, if you say the hardness of perlite, then the hardness could be a volume fraction average hardness. How? So, the hardness of perlite, I could say, if it is denoted as H, so I could say alpha into H of ferrite plus 1 minus alpha into H of cementite. And this H essentially is an effective H, and that effective H is based on the volume fraction, and sometimes you can encounter, for example, when you have different systems or different mediums or different substances, then an averaging may be necessary, and this could be volume average, this could be work fraction average or mass fraction average. In the case of temperature, we have seen that volume average temperature or volume average heat flux, we do time averaging. So the D effective is also in such context, because we have one material, the diffusion is taking place, and we have to calculate the rate. So should we use the bulk material diffusion coefficient, or should we use the diffusion coefficient through the grain boundary? And in such context, a effective diffusion coefficient, which is essentially an area average. So the averaging, this is done by assuming continuum approach. This is okay. So this here it is volume fraction average hardness. On the other hand, when we will determine the effective diffusion coefficient, particularly in a polycrystalline material, we basically use an area average diffusion coefficient. Let us quickly see that what it is. Now suppose I have two different materials. So one is this, and this is and the other is drawn with maybe is this. So we are considering basically a parallel diffusion, and it is this particular surface, okay, as you can see here, which is an interface between the two. Okay. So we have, through this phase the diffusion is taking place along this direction, through this phase the diffusion is taking place along this direction. So you can imagine, suppose if I have exactly the same thing I wanted to draw, there are one duster here, the other duster is here, and that's what it is basically I want to do. Okay. So diffusion is taking place through this surface and diffusion is taking through this surface. They are doing, it's a one dimensional diffusion case towards me, and you can see the planar areas. Okay. They are more or less the same areas through which the diffusion is taking place. We assume that the concentration gradient is similar here. Okay. So whatever, there is no cross flow here, it is a one dimensional diffusion in this particular direction. So the diffusion takes place along this direction, which say is the x direction, and then we have the concentration gradient here is exactly identical to the concentration gradient. Now, so therefore I can say that one is this, which is J1, and the other is this, which is J2, and this flux values we can say that J is a solid state diffusion, so we don't have to write the generalized equation. So the diffusion flux is totally equal to the J is equal to N. Okay, that's what it is. So the J1 is equal to, I can write, which is equal to D1 divided by L1, and then we can say that it is, no, we will not write this, D1 into D and C of 1 and dy. Suppose this is my y direction. That is the. Similarly, I can say J2 is equal to D2 into dC1 and dy. So let us not write, because I assume that the concentration gradients, this is an assumption based on which this analysis is presented. Okay. So therefore, we can say that the n of I now is equal to j of I into A of 1. I have taken these two dusters. Okay. So now I consider that this area is A1 and this area is A2. That's what it is. And we assume that dC, and this is J2 into A2 is equal to N2, and this is equal to D2 into A2, the same concentration gradient. So the total rate of transport now is Ni plus N1 plus N2, and that essentially represents is equal to minus d1a1 plus d2a2 is equal to multiplied by the concentration gradient. And then if you say that I want to now calculate the area average flux, then I will say that I will divide it by the total area in which A0 is equal to A1 plus A2, and this I get as minus D1 A1 by A0 plus D2 into A2 by A0. So what you see here, A0, A1 by A0 is a fraction. So this is an A2 by A0 is another fraction. So I could have written that A2 by A0, okay, if it is F1, the fractional area. So if I can write that N1 plus N2 divided by A0 is equal to minus D1 into FA1, then I would say that this will come out to be 1 minus FA1 into D2 multiplied by DC dy. So this is the fractional area A1 by A0, and therefore I can write this parameter because A1 plus A2 is equal to A0. So I can also write, and as you can see here, earlier what I had alpha into HF, now you can say F1 into D plus 1 minus FA1 into D, exactly 1 minus alpha into HC. So two different D's here, hardnesses were the different components, the diffusion coefficients are the different for the different materials, and they are multiplied by the area. So that's why this parameter now is known as D effective, the area average diffusion coefficient. Now let us quickly see in 2-3 minutes time what does this indicates. What is the value of effective diffusion coefficient, because we have done it this much. So you can make a very simple kind of a exercise finding out the area of the grain, etc. Will be very difficult, but we can do an order of magnitude analysis in this particular case. Now if you say that you have a square grain, it doesn't look square, so let me make it square, square grain, okay, and then we have these are the yellow ones are the grain boundaries, okay. So this is the grain boundary, and then again we have another grain here, and then we have that's how the grains are. I am not drawing beyond this, so you can imagine the yellow ones are basically the grain boundaries, okay. And now I want to find out that if you have such a cluster, n number of such squares grains, okay, and this is the some kind of a scheme where I have W as the length and breadth of the two-dimensional grain, and delta is the length or the thickness of the grain boundary, then I want to find out that what are the relative areas, okay. For example, if I have n, let us say that there are n total number of grains, and I want to do this analysis. So the area of grains, which we call it lattice area, AL, will be is equal to n into W square, because W is assumed to be square. So W into W represents square, there are n such elements, and then we get. What is the grain boundary? The grain boundary area is going to be 4, each grain is surrounded by, because it is a two-dimensional figure, you must understand. So it's 4, then it's multiplied by n into delta into W, okay, and this should be, because each grain boundary is shared between two and therefore I divide it by 2. So therefore this becomes is equal to 2 ND into W. Now, if you look at the ratio, so therefore a grain plus a grain boundary, that becomes is equal to N W square plus 2 times delta into N into W. So therefore, I will write that A0, A1 or A grain by A total or A0, so which is my A0, okay, and A0. So this becomes is equal to area of the grain, so that is NW square is NW square plus 2 delta N to W, and then we have A grain boundary by A0, which is equal to 2 delta NW and divided by NW square plus 2 delta NW. This appears to be, now if you divide it by this will come out to be 1, dividing all through by NW square plus 1, and then we have WW, NN cancels out, then you have 2 delta divided by W. And this comes out to be, as you can see here, A grain boundary. So this is, if you divide it by this, so this will come out to be 1 divided by 1 plus we have W by 2 delta L. 2 delta. What does this indicate? This indicates that area grain by A0, because W is much greater, the size of the grain is much greater than this thickness, the grain boundary. Okay? So therefore I can say with respect to 1, this is less than 1, so this is approximately of the order of 1. On the other hand, what is this? This is equal to, because delta is much bigger, so this becomes a number which is obviously much greater than 1. Okay? 1 can be ignored, so then the delta goes above, okay, and then divided by W, delta is small, and therefore we should be able to say that this parameter is actually much greater than 1. So the grain boundary area comes out to be, okay, so this is, I hope you understand it. So what I have done, I have taken the ratio, then I have divided it by NW square. So you got 1 here, and then we get NW square. So W is the, W from W square it remains, and 2 delta remains here. Similarly here we have 2 delta NW plus the total area divided by this. So this is 1, okay, and then this divided by the factor 2 comes here, the delta comes here, and then we have the W which is remaining from W square itself. And if we look at this, so as I have indicated, W is larger than 2W, okay, 2 delta. So this parameter is very small. So 1 plus a small parameter will be of the order of 1. So therefore I can say this is of the order of 1. This is, on the other hand, is a very large quantity, okay, because delta is smaller. So therefore this is essentially equal to delta divided by 2 delta. So I would say this is equal to 2 delta by W. Because this term dominates, 1 could be ignored, so the 2 delta goes above, and this is equal to 2 delta. So therefore if you go back to this expression, the effective diffusion coefficient, so the effective diffusion coefficient now becomes equal to, we have, so the grain boundary part is the diffusion coefficient of the grain, and then the area fraction is of the order of 1. And then here we have 2 delta by W into the diffusion coefficient of grain boundary. So the effective diffusion coefficient will be dominated by the grain bound, the lattice diffusion. This is also termed as DL, the lattice or the grain diffusion through the grain, dominated by the lattice diffusion or diffusion through the grain, provided this term dominates over this particular term, or the converse is 2. Okay? If this term is greater than this, in that case, we will say that the grain boundary diffusion really dominates. But as I have indicated, because the grain boundary contains lot of defects, so as a result of which what happens, this term happens to be much larger than this term itself. So this is going to be a determining factor in order to, determine the total weight of the effective diffusion coefficient in terms of the two respective diffusion coefficients of the grain and grain boundaries. We will continue.